welcome to the Pioneer STEM Show. How are you doing?
I'm fine.
Let's get to meet you. What is your endeavor? What are you about? Tell me about yourself.
Okay, so I'm an aspiring robotics engineer.
Okay, amazing.
400 level Covenant University. So I implement novel research papers so that I can build cool projects relating to the field of robotics and artificial intelligence.
Amazing. Give me an example of a research paper that you've implemented.
A research project I'm working on uses a research paper on visual SLAM. That is visual simultaneous localization and mapping. So that enables robots to be able to map out their environments while knowing where they are.
This sounds like machine learning, if I'm correct.
There's an element of machine learning in it, but most of it is triangulation and computer vision.
Okay, so do you use autopilots, or how do you make your drones autonomous? Because that's what makes drones. The fact that they can perform certain tasks themselves. So what system do you use, autopilot, or what other alternative?
I write my software myself.
Wow, that is so impressive. What language, I must ask?
C++.
C++. I was expecting you to say Python, because that's like the foundation of every coder. That's incredible. So tell us, what projects do you bring to us today?
Okay, so today I brought my drone.
Okay.
So my drone is an autonomous delivery drone.
Does it have capacity for payload?
Yes, but I haven't yet implemented a cargo compartment and a detach system. I'm still working on the autonomous flight navigation.
It's incredible. I was just talking about drone delivery, and here we are. That's what you actually do. Yeah. Fantastic. So tell me, how did you start this? How did you get into drone programming and all of this?
Well, I first started my first Arduino project last year, April.
Okay, so you started with Arduino?
Yeah, I started making Arduino, blinking LEDs, potentiometers, and so on. So over time I graduated because Arduino is fairly simple.
Okay.
So I used to wonder, like, what is actually going on behind the hood of the Arduino framework. For instance, Arduino kind of simplifies a lot of programming. Like Arduino deals with timers and communication protocols to watchdogs and buses.
Yes.
So I started researching about deep embedded systems. So I got to know about the STM32 microcontroller, and now you can do pretty advanced stuff with it. So I was looking for what I normally learn from are projects.
Amazing.
So I was looking for quite an advanced project, but it's something that is still beginner friendly for me to learn more about advanced embedded systems.
Can you give me an example of a project of that nature?
A drone, for instance.
Okay. So this has been also a major learning process for you.
Yes.
Fantastic. So using all that you've learned so far, what do you aim to achieve prospectively in the coming future?
My current goal right now is majorly learning. I haven't really focused on whether transportation or the medical or the healthcare or agriculture. I'm focused on learning right now, because if you know your stuff, you can transform any area. You can transform any area of robotics.
Yeah. So what would you advise someone who does basic Arduino projects to going into deep and advanced stuff like you do? I mean, you're talking about deep learning and talking about you write your own code for autonomous.
Yeah.
That's incredible. So explain to me how someone watching right now, how can they go from blinking LEDs to building fantastic projects like you do?
Okay. Just be curious. My advice for anyone starting out in the field of robotics or embedded systems, always be curious and always do what you like doing. Always like learning. So be curious about what makes things work. Be curious about how the Arduino framework is working.
Okay.
Be curious about why things work in general. And the more curious you are, the more you want to learn. The more you want to learn, the more projects you take on, the better you get. So for stuff like autonomous drones and autonomous vehicles, they can't just start working by themselves.
Correct.
Something has to make them work.
Yes.
You can either use AI or you can hard code the set of instructions into
pre-programmed.
Yeah. So now AI, how does AI learn? That's another rabbit hole to go into.
Yes.
So I've started out with AI actually. I was wondering how can machine learn? I used to think that AI was just if statements.
Prompt.
Yes, like if this, then do this. If this happens, then do this. If this
Okay.
happens, then I found out that there's actually maths behind AI, and I'm like, how come? How does mathematics turn into ChatGPT? Like, where does it? So I was curious about that, so I started diving deep. I started taking courses on deep learning. I built my first neural network 2022 September. Then I didn't know I would go anywhere because it was just a simple neural network to classify. I can't even remember the project, but it was a very simple neural network. Over time, as I took on more projects, I began learning. Another advice: go deep into what you are doing. Don't be satisfied with the surface level results. Try and implement what the top researchers in the field are doing.
Okay, so do you advise people to specialize rather than just generalizing what they learn?
Yes. At first, generalize, like learn, know about, know something about all things, but
Okay.
know very well about something.
So I want to ask you, as a Nigerian prospective robotics engineer, what challenges have you faced in your journey so far?
My challenges.
Yeah.
Well, sometimes it's not going to be easy because while your friends are playing, while your friends are having fun, you'll be there battling with
Bugs.
battling with bugs. Like it's just one bug, it's just one line of code that will make the entire system not to work.
Yeah, I
So
relate to that.
it's like you marry your machine. So while people are having fun, you'll be there learning and digging deep. I mean, if you spend t- if you spend time on something, you eventually start to like it. Another challenge is learning, because those research papers, it's from top PhD researchers at universities like MIT, Oxford. So it's really hard. It's really hard to pull something from there to make your own project.
Let's say a 13-year-old guy or a lady, a young girl, is watching this right now and is asking, how do I get the materials to do my own little drone? How do you source for equipment? How do you source for materials? How do you source for intellectual information that you use?
Well, I buy my materials. I buy my components locally here in Nigeria. If they aren't available in Nigeria, I order them abroad. So yeah, that is another major challenge I've faced: the lack of components and also the price and the lack of components and costs.
Amazing. Thank you so much. It's been so insightful getting to know you, getting to learn about what you do. Thank you for coming on the Pioneer STEM show. Thank you for sticking with us. We still have more. We're going to be showing you some amazing projects. Don't touch that dial. We'll be right back. Welcome back to the Pioneer STEM show. You're not ready for what you're about to see. Timmy, what am I looking at?
So these are two of my projects. One
Okay.
is a drone, one is a car.
Okay, so please walk me through the design and construction of this drone, especially.
This drone especially. So everything starts with the propellers.
Okay.
So for a drone to fly, it must have propellers, because propellers are what push the air down, which creates an opposite reaction force, which makes the drone stay afloat.
Amazing.
So while the drone is pushing air downwards, it's staying afloat.
Trust.
Yeah.
Yeah. Fantastic.
So now, for that to happen, you have to be able to set the speed of all the motors. And while you're like, the drone has to know where it is in space for it to balance properly. Because if it's like this, okay, so let me explain how the drone moves.
Okay.
If the drone wants to move forward, it increases the speed of the back propellers and reduces the speed of the front propellers. So when the drone is tilting forward, you can see that these guys have reduced their speed. So you can see that it's angled towards the front. So it moves forward like this because the propellers are facing forward. So if the drone wants to move backwards, it increases the speed of the front propellers. Let's say this is the front. So when the speed of the front propellers increase, obviously this part will rise higher than this part.
Yes.
So it will create a moment in the drone which turns the drone backwards, and the resultant force is in the back direction. If it wants to move left and right, same thing. Well, if you want to turn it in the air, so since this propeller rotates clockwise, this rotates anti-clockwise.
Okay.
There's a law of science that angular momentum is conserved. So if a propeller is rotating anti-clockwise, the drone itself won't rotate clockwise. So that if this is rotating clockwise, this is anti-clockwise, this is clockwise, this is anti-clockwise, the drone will be stable.
So torque is cancelled.
Yes, so torque is cancelled out. So what happens when you reduce the speed of the propellers rotating anti-clockwise? Resultant from the propellers rotating clockwise will be greater than the torque of the propellers rotating anti-clockwise.
So we're talking about difference in torque now.
Yeah, difference in torque. So since this rotates clockwise, and this is rotating, and this is the torque produced by this is more than this.
Yes.
Then the resultant torque on the drone will be anti-clockwise. So the drone will be able to yaw anti-clockwise.
Okay, so I'm seeing so many wires here. Yeah. What am I looking at? Can you explain that, that?
So this is the major guy on this drone. Actually, this is the major guy on this drone.
Okay.
But we'll get to that later. This is the major computer for the basic drone operations. That is just keeping the drone afloat.
Okay, so this drone has its own computer.
Yes.
So this is a mini computer.
It's not it's a controller.
Okay.
So microcontroller. Microcontroller.
Okay.
This is the computer.
Okay, so this is Arduino. This Arduino.
STM.
So this is more like a calculator. This is more like a computer.
Computers are calculators. So
yeah, but in terms of simplicity and complexity, this is more complex.
Yeah. So
if I'm getting you right, this is more simple.
Yes.
Okay, amazing.
But ironically, the code for this guy is more complex than the code for this.
Why is that? This is coded in Python.
No.
What is it coded in?
It's C++ also.
But this is Raspberry Pi.
But yeah, it's Raspberry Pi.
But their primary language is what?
No, you can use Python or C++.
How about this one?
This one is C++.
Okay, is that why it's more complex?
No, it's more complex because you have to start manipulating the registers, the timers, the watchdogs.
Okay, so this is more straightforward.
Yes, it depends.
Okay.
The control algorithm of this is more complex than this, but the code of this is more complex than this. For this to work, I use a framework called ROS. That's Robot Operating System.
Okay.
ROS2 actually. So the ROS2 allows me to implement stuff like motion planning, path planning, computer vision, mapping and localization.
So who handles all that? This?
Yes, this.
Okay.
This just pulls data from all the sensors. This is a barometer. This purple thing is a barometer.
Okay.
This blue big one is a gyroscope and an accelerometer. That's the MPU 6050.
So that controls what? The motion and the orientation?
No, that senses the rotation, the angular rates, and the acceleration of the drone.
How about the barometer?
The barometer just senses air pressure.
Okay.
So now, those are sensors. They just sense physical changes in the environment. It's up to the programmer to do something with those readings. So now, altitude varies inversely proportional to air pressure.
Pressure.
Yeah. So the more the pressure, the less the altitude.
Okay.
The less the pressure, the more the altitude. So if the altitude of the air around the drone reduces, the drone will know that it's in a high position.
So what do you do with that kind of information?
So I can use it to set the height at which it should hover.
Okay.
The barometer allows the drone to know its state, its orientation in space. So the gyroscope measures the angular velocity of the drone. If I integrate the angular velocity of the drone, I'll be able to get the angle of the drone. The accelerometer also measures the angle of the drone.
Okay.
But that one measures the angle directly. So the gyrometer, all these sensors are noisy. So we have to do some filtering in order to get in order to get good state estimation. So I combine the gyroscope and the accelerometer with a Kalman filter,
Okay.
which is a very smart filter that allows the drone to be able to know its orientation in space.
Okay, so for now to be able to communicate with this drone, I assume you need a transmitter and a receiver. So what are you doing? What is the system like here?
Okay, so this is the transceiver.
Is this an NRF?
Yeah, it's an NRF24L01 module plus.
Okay. What do you mean by trans receiver? What does that
So
mean?
it can send. So there's a base station on the ground.
Mm-hmm.
It sends and receives data from that base station. Stuff like altitude, the temperature, the set location, the remaining battery, the remaining flight time, and stuff like that. So, and I can send commands from the ground station to the drone using this So because it's a transceiver, it can receive and send data simultaneously.
That makes sense. So from the whole explanation you've made, these guys get the readings, this guy processes it, this guy sends and receives to your base station.
Yes.
Okay. All right, so let's talk about the use case of this drone. You made mention that it should have a payload system.
Yes.
Okay, can you tell us more about that?
So when I'm done with this, there will be a payload, there will be a cargo compartment, which will have a latch. So I will be able to tell the drone to go to a specific location. It will be able to take off by itself, go to that location, land, drop off the cargo, take off and return back to the place it took off from. This can be used in a lot of applications. For example, delivery. Drone deliveries will approximately, they will take less than 10 minutes or 30 minutes. So if you order something for a store, an online store now, all they have to do is just put your package in a drone, takes off, goes to your house, drop it there, come back.
So that's what this does.
That's what it's capable of doing, yes. Also, it can be used in the security, field. For example, surveillance. The drone can perform preset operations. It can perform preset missions. So it's able to take off by itself to a particular location and survey the entire area. Maybe it will be using this camera to be able to detect threats or suspicious activity.
Areas of interest.
And to be able to come back and land.
Mm.
Agriculture. The drone can be used to detect pests or to be able to count the number of fruits that are ripe in a farmland. It can also be able to, farmlands are vast, and so farmers can't be going to every area all the time. So you can be able to monitor all the crops, pest activity, intruder activity. It can also be able to get there are various sensors on the drone. So it can be able to determine the humidity, the air pressure, the temperature of different areas of the farmland. There are other,
Okay, so walk me through, we've spoken about the aerodynamics, we've spoken about the microcontrollers. Walk me through the software. Walk me through how you programmed this thing from scratch to finish.
Okay.
What was the experience like?
Wow. It's a very steep learning curve. I mean, anyone can make a drone fly.
Yeah.
But it's very hard to make a drone autonomous. The balancing the drone on its own, there's something called the PID controller. So if you want the drone to hover, you don't want it to tilt left or tilt right. There's a controller that enables the drone to stay in the position you want it to be. Let's say something like wind blows the drone. It's maybe like turn left. So the controller is able to bring it back. What we use is the PID controller. It takes the current state and the desired state, calculates the error between those states, and it outputs motor controls to bring the drone back to the desired states.
That's beautiful. So I understand that. How effective is this PID? How effective is this system to actually make it autonomous? Because I can imagine that drones like drone companies like DJI, they use satellite connection to achieve some of the things you're saying. So how are you able to do all of that in this?
Yeah, so this is a GPS receiver.
I was wondering how. Okay.
Yeah, so
nice.
This is what gets data from the satellites.
Okay, so you do have satellite connection, GPS.
Yes.
Okay.
Yes.
Because I imagine this is not RC, right? This is autonomous. How do you take off? How do you hover? How do you go to a point of interest? How do you come back? Walk me through the process of doing that.
So from my ground station, let's say the drone is on my ground station, and this is not my ground station. This is just a control. This is
A human pilot.
yeah, it's a human. But from my ground station, let's say my ground station is here. I input the commands. I just specify the location where it should go to.
Okay.
Then I specify whether it should land there, whether it should return. So that gets sent to my, and I specify the altitude at which it should fly at. So that gets sent to my drone from the ground station to the receiver. It goes to the microcontroller, that's the STM32 microcontroller. The STM32 microcontroller is connected to the Raspberry Pi 5 using universal asynchronous receiver and transmitter. That's for me of UART. The Raspberry Pi has a map of the environment. Given the coordinates I set on my ground station, it calculates the distance between where it is. So it pulls its current location from this GPS. So using that PID controller, so the PID controller can be used for both the attitude, that is the orientation of the drone, and the location, that is the translational position of the drone.
Okay, so tell me about the attributes, physical attributes. How long can this thing fly? I'm seeing a 4,200 mAh battery. Is that what you use?
Yeah.
So how long can you stay in the air?
It can stay in the air for approximately 40 minutes.
Wow, that's more than my DJI. Yeah. So also, how high can you fly?
Maybe a height of 100 meters.
Okay, that's fair enough. Thank you so much, Timi, for this amazing insights into your technology. That was so insightful. I learned so much about drones. Thank you so much for joining us. Don't go anywhere. We will be right back.
Awesome. Timi, as an undergrad, has surprised us. He's done remarkably very well. I mean, David, you ran the show from beginning to the end almost, right? So what do you think about this young man?
I mean, I've learned a lot about drone. I'm into that field myself.
Yes, you are. I
have to say, I can't wait to see the application of this kind of tech in the Nigerian security system as a whole, law enforcement, and even like we see in the US, drone delivery. There's so many potential to this kind of. So I celebrate Timi, an incredible young man.
Absolutely, and I think our government should invest in young minds like Timi, to keep making and doing things for the country. It's a proud moment for us here on the Pioneer STEM Show.
Yes, it is.
So a big shout out to all Covenant University students and lecturers, and of course to all family and friends of Timi. It's a time where we draw the curtains right here on the Pioneer STEM Show. But we'll see you same time, next video, next week. Don't you touch that dial.